I'm Sayed, a PhD student at Catania University. Today I want to talk over our recent research on the finite element model calibration of existing bell tower located in Aci Castello, Sicily. This research is the continuation of a previous research on model calibration of this structure, where the model was calibrated manually based on trial and error. In this research, we try to automate the calibration process utilizing meta-heuristic algorithms, including particle storm optimization and genetic algorithm. The finite element model calibration is the process aiming at adjusting the numerical model so that it accurately and more precisely reflects the measured behavior of the real structure. So usually it is defined as a minimization and optimization problem where an objective function which quantifies the discrepancy and difference between the modal parameters, or also it can be also static parameters, but mostly dynamic properties such as the frequency and mode shapes of the numerical model and the real structure. So there are, in general, there are two ways for calibrating the finite element models. The manual one, which is based on trial and error, is done when the structure is simple and it requires engineering judgment, and it's a time-consuming process. For our case, which is it's almost a complex structure, we try to automate this procedure utilizing the meta-heuristic algorithms. In general, finite element model calibrations are divided into main groups: non-iterative or direct methods and iterative or indirect method. The direct method, in the direct method, the structural stiffness is updated, and it is a direct method, and it's not repetitive and iterative method, and it is usually used when we want to have the computational efficiency. The iterative method, which is widely used nowadays, are divided again into deterministic maximum likelihood methods and stochastic uncertainty quantifications. In deterministic methods, the problem is defined and converted to an objective function, as I told you before, which is the quantification of the differences between the numerical model and the real structure's modal properties. And there are nature-inspired methods such as simulated annealing, ant colony optimization, genetic algorithm, and particle storm optimization that today I'm gonna present my work on the two methods of genetic algorithm and particle storm optimization. And other methods are stochastic methods that the problem is behaved and addressed like a statistic challenge. The case study of this research is bell tower of San Giuseppe in Aci Castello, in municipality of Aci Castello in the metropolitan city of Catania. It dates back, its construction dates back to 1748. It has, the height is 15.4, and it has a rectangular section tapering the tapering to 3.8 by 3.3 from the height of 2.5 to the top of the tower. And it consists of three main parts with different quality of the material. The lower part with higher quality masonry with larger, coarse or roughly shaped lava stone, which arranged in pseudo-regular rows with cohesive hydraulic lime mortar. The middle part has medium quality masonry, which is also in good order and arranged in a pseudo-regular rows with cohesive lime mortar. And the upper part has the lowest quality with very low quality mortar and a small lava stones and bricks that has the worst quality in the structure. So for the dynamic identification using operational model analysis, the frequency domain decomposition were used, and this research take advantage of the results of the previous study, and the 6 velocimeters, Tromino sensor, were mounted at 3 levels of the height of the structures in order to record and capture both bending and torsional shapes of the movements of the structure. It was supposed to, we were supposed to model the structure in mesosphere. It was the first step for the modeling and analyzing the structure, but there was a problem with mesosphere that it wasn't linked to other environments for coding and scripting. So for detailed finite element modeling, we created the model and developed the model in mesosphere, and then the model was translated to OpenSysY utilizing transformation of nodal information, element connectivity data, and material information by utilizing the scripting capabilities of OpenSys based on Python using Pandas library. So about 36,000 4-node tetrahedral elements were utilized, and for the verification of the both models, the periods and nodal information were compared to each other. And as you can, you're observant here, the results of model, operational model analysis, which is the natural frequencies for first 3 modes, along with the mode shapes, are presented here, and the eigenvalue analysis were performed in both softwares. And as you can see, the first and second modes are bending modes along east-west and north-south direction respectively, and the third mode was torsional mode. This is the flowchart of the research. This is an iterative process that genetic algorithm and particle storm optimizations develop and evolve in different for the next iterations, and calculate the objective function. 2 objective functions were considered in this research. First, solely based on the frequencies, and the second objective function were based on the weighted residual of frequencies and mode shapes. And MAC is the model assurance criterion, which quantifies the discrepancy the degree of similarity between mode shapes. For the validation of the methods, two-phase approach was utilized. At the first stage, the output of the initial finite element simulation were considered as experimental data in order to check if the genetic algorithm and PSO are able to recover the known parameters that we already used for the initial model. And the second phase is utilizing the real data for the real calibration of the structure. And two objective functions were considered. The first one was only based on frequencies for the first 10 modes, and the second objective function was the combination of frequencies and mode shapes only for 5 modes and with the coefficients of 0.7 and 0.3, because for frequency we are more confident about the results. And 5 regions were considered in the structure with isotropic materials, so elastic moduli, Poisson ratio, and unit weights for 5 different regions were considered the candidate parameters for updating. And for genetic algorithm, 200, I will skip this part later. If you have a question, I will answer the question. This is the results of the both algorithm for the synthetic data and for the test of the data. And in the next slide, I have make better visualization, which is the error between the estimated parameters and the initial the input of the finite element model. As you can see, the blue colors are genetic algorithm and PSO under F1, which is the first objective function only based on frequency, and the red and orange one are second objective function for both algorithms. As you can see, for the second, for the both algorithm, when we use both frequency and mode shapes, the error decreases significantly, and also for the most parameters, GA outperformed PSO for the different parameters. And this is the results of the actual data, and for the actual data, we only had the frequencies, not mode shapes, and this is the trend of convergence of the genetic algorithm. And the next stage of our research is utilizing orthotropic material, because we can add more constraint to the problem, and also for increasing the quality and the speed of the convergence and the analysis, we are trying to use surrogate model for the quicker analysis and going towards digital twin of the model updating. I'm sorry, I had to skip some slides in order to give you time for question. Thank you very much.